All right. There we go. So guys, it is our last SI session of the semester. Congrats on making it this far. Hopefully you are feeling confident going into the final. If not, well, we can work on that. You don't have a lot of time, but we still have this one session left. So with that in mind, let's just get straight to it. And the first thing we're going to go over today is the promise I made yesterday, which was to explain in layman's terms, so to speak, why logarithmic differentiation works. So it's actually a very interesting reason why logarithmic differentiation works. And I did have to do a good bit of looking into it, and I spent all morning messing around just trying to figure out a really good way to explain it. And this was the conclusion that I have come to. So the derivative of the inverse of a function is equivalent to 1 over f prime of the inverse of the function, of the inverse of f of x. And I went through and tested it, and it does work. I plugged in the values for like x squared, and then I went, okay, that's pretty cool. So I was like, now I know that that has to be relevant to logarithmic differentiation, because logarithmic differentiation, the inverse of the function, the inverse of the function is e to the x, and that's, Tony, sorry, y'all, my cat's moving the board. Go away, Tony. No math for cats. Okay, where was I? So the reason that logarithmic differentiation is special is because the inverse of the function is e to the x. And as we all know, the derivative of e to the x is quite simply just e to the x. So what that means is that when you're doing a logarithm, like when you're using logarithmic differentiation, it's taking advantage of the fact that the derivative of the inverse of the function is equal to the inverse of the function, meaning the inverse of the function is equal to the inverse prime of the function. So what that allows us to do is it allows us to differentiate it and, not really affect the problem, so to speak. Meaning if we try it, we can't do that same rule with the inverse function over here, because the inverse of the function, the derivative of the inverse of the function, is not equal to the inverse of the function. And that's for x squared, so we know that the derivative of x squared is 1 over 2 root x. Or no, the derivative of the inverse of x squared, my apologies, is 1 over 2 root x, because the inverse of f of x squared is equal to root x. So the inverse of f is the square root of x, and the derivative of that is going to give us 1 over 2 root x. So with that in mind, we know that the function is x squared, the inverse is root x, the derivative of the inverse is 1 over 2 root x, and the derivative of the function is 2x. So the reason that this logarithmic differentiation technique can't be used with just, we can't use it in any directions because of e to the x here. And the reason we can exploit this rule at all is because the derivative of e to the x is e to the x. And differential equations has a similar thing, but we're not going to go into that because you guys have a final. So I just wanted to show you guys the math behind logarithmic differentiation, in case any of you just needed a better grasp of it. So I'm going to erase the board now, and the next thing we're going to be looking at is concavity using the first and second derivative test. Then after that, we're going to be looking at some related rates problems, and we're going to finish the day off with integration, just a little bit. Integration should be, none of the problems on integration should be especially challenging for y'all, because it is just the opposite of a derivative. So you really already know how to do it. You just gotta do it backwards. All right, so for concavity, what we're going to do is I'm just going to give you guys a rundown of how to go through the steps, and I'm going to kind of explain each one. So I actually sent you guys a picture of this handout, and if you want to reference it, you can. If not, I'm going to be going over it regardless. So the first thing we're going to be looking at is this is how we are able to determine the intervals of concave up, concave down, and identify inflection points. So step one, find the domain of f. Of f. Step two is going to be compute the second derivative. And this is just because for these problems, if the first derivative test isn't convenient, then you might want to use the second derivative test. If the second derivative test fails, then you're going to want to go back to the first derivative test. So it's always just going to be useful to get the second derivative right off the bat. I know you might not always have to, but it's just a good habit and it'll probably build discipline. All right, let's see what step three is. So step three says find possible points of inflection, and what that means is find all numbers c in the domain of f, where f double prime of c is equal to 0. So find critical numbers, critical values, and we'll put in parentheses beneath that f prime of c equals 0. After you do that, you're going to want to divide the domain. So the points of inflection, we are going to divide the domain into subintervals. So use subintervals to split domain. Divide, split, whatever you want to say. Step 5, select test value. So pick a test value in each subinterval. So I'm not going to write that down. Step 6, determine signs. Determine the sign of f double prime of whichever value we chose for the test values. Apply concavity test. So here, this is the important stuff. Based on part 6. All right, nice. So here's the juicy stuff for this section. So f prime of whatever value, which out of the critical numbers / endpoints you selected is greater than 0, then concave up. And this is for that subinterval. F prime of c is less than 0, concave down. All right, identify inflection points. So check if it is an inflection point. This will happen if concavity changes at c, comma, f of c. So check, final step, we'll just say, call this step 5 right here. Call this step 6. Check inflection points. And we'll use c, comma, f of c. Okay, and I'm just going through a quick rundown of that because this stuff should be pretty straightforward. I mean, you guys have done a lot of these types of problems at this point in the semester. So what I'm going to do next is, let's just write down some important stuff because you know what? Let's do that too. So next step, I'm just going to write down stuff y'all should know. Yeah, so that's what I'm going to do next. And then we're going to look at some specific problems. Because you know what? I want this to be useful in a way that it makes you learn from it, but at the same time, I want it to have utility. So let's not waste any time and let's make sure you all get A's in this class. Okay, so let's review some things. Derivative of a constant. I don't like that, that's not nice. is 0. The power rule states that d dx for x to the n is equal to n times x to the n minus 1 power. The derivative for two functions being multiplied together, this is known as the product rule, is equal to f of x being the first function times g prime of x being the derivative of the second function plus f prime of x, the derivative of the first function, times g of x, just the second function. Now the derivative for the quotient of two functions, this is the quotient rule, is f prime of x times g of x minus g prime of x times f of x divided by g of x squared. Okay. Chain rule. This is the derivative of a, why am I blanking on this word? The derivative of a composite function. There we go. So that is equal to f prime of g of x times g prime of x, where f prime is the derivative of the outside function, that is f. G of x means that the inside stays the same. G prime of x means that we multiply the entire thing by the derivative of the inside to finish the chain rule. All right, let's see. So that is all of our basic rules of derivatives. With that, let's look at some trig rules real quick. And I expect all of you are writing this down because you don't need to write this down if you already have that. That was basic, but all of this stuff will be useful. If you know it well, then you shouldn't have trouble on the test. So now let's go over trig derivatives. Yes. So d dx for sine of x is equal to cosine of x. The derivative, oh wait, just kidding, it's, yeah, no, why would I, yeah. Cosine of x is equal to negative sine of x. Why am I using this sheet? I'm making myself stutter. The derivative of tangent of x is equal to secant squared of x. The derivative of secant of x is equal to secant of x times tangent of x. And these are probably the only ones you're going to run into. You probably won't see a cosecant or a cotangent on the test, but knowing that they're trig properties, they follow a similar pattern of that. You know, you can derive all trig derivatives from another trig derivative. But this right here is probably the thing that you guys will all forget, and I feel like it might be on the test. I don't know. Some professors like to do this a lot. Some professors don't like to do it. But this is something that you should have memorized. So the derivative of sine inverse of x is equivalent to 1 over the square root of 1 minus x squared. The derivative of inverse of cosine of x is equal to negative 1 over the square root of 1 minus x squared. And the derivative of the inverse of tangent is equal to 1 over 1 plus x squared. There we go, x squared. Okay, so that right there, this is stuff you should have memorized. Blatantly memorize this. Make flashcards, sleep with it under your pillow, do whatever you have to do. Make sure all of this stuff is memorized because it will just save you time on the test. And time is of the essence when it comes to calculus tests. At this point in the semester, I am sure you are all aware of that. All right, so let's go over a few more derivatives and rules and stuff. Then we'll work a few problems on related rates, integrals, and then we will call it a day, and I suppose a semester as well. Okay, exponential and logarithmic functions. So some of these I actually don't have memorized, which I definitely should. This one right here, I didn't have this one off the top of my head, but I'm gonna make sure to have it in my vocabulary for next time. So the derivative of a constant raised to x is equal to that constant raised to x times the natural log of that constant. All right, next, this one should be, you guys should all love this derivative because it's the easiest one. The derivative of e to the x is e to the x. So then with that in mind, we've got the derivative of ln of x, which is the inverse of e to x, but the derivative of that is 1 over x. And then, of course, the derivative of a log with a base is going to be log a x is equal to 1 over x times the natural log of a. Okay. So those are just some more derivatives. Out of these ones, you probably only need to know these two, but those other ones are useful to have, just in case your Calc 2 teacher is harder than your Calc 1 professor currently is. Okay, we did a lot of implicit differentiation yesterday. Let's see. Log differentiation, we did do that, and now you guys understand how that works, I'm sure, on such a deep level that you just love the way that logarithmic differentiation works. Okay, so let's do some optimization. I'm going through making sure that we got everything up to that covered. Some related rates type problems. All right, we've gone through all of that. So let's do this one. Yes, we'll do a related rate problem. I'll go over everything for integration that you need to know. By the way, I hope that you did write down all of those differentiation properties like derivative of e to the x, and I hope that you're aware that that would also mean that the integral of e to the x is equivalent to e to the x, because the integral is just a backwards derivative, essentially. All right, so our question says, when you have a box has square sides of side lengths x and a height of h length. So square, or actually, you know what? It's a box. So cube, side lengths. Wait a minute. Height, h, x and h are changing time. Okay, so square base, height of h. There we go. Square base with sides x and height h. So it says, suppose that x and h are changing in a time. At that instant, we have x equals 4 inches and h is equal to 7 inches. The base side length x is decreasing at a rate of 1 inch per hour, and the height h is increasing at a rate of 2 inches per hour. So dx equals negative 1 inch per hour, and then dH equals positive 2 inch per hour. Okay. Find the rate of change of the volume of the box. At the moment, it is 4 by 4 by 7. Is the volume increasing or decreasing? So volume up or down? So that is a spicy problem right there. Let's see how we should approach it. So we have a box with square base. All right, so we got a square base here with sides x. That means that its width and its length are the same, but it is a cube. So I'm going to draw that a little lower down. Since it's a cube, we have to think in terms of h as well. So we got that, that. And this is x, that's x, and that is h. Okay. So x equals 4 inches, h equals 7 inches. The derivative of x is negative 1 inch per hour. The derivative of h is 2 inches per hour. They want to know what the volume of the box is. They want to find the rate of change of the volume of the box at the moment that it's 4 by 4 by 7. Find the rate of change of the volume of the box at the moment. Okay, so this one looks tricky because we have two variables, but they gave us all the information for the problem. So this right here is a problem that is just meant to look intimidating, but is actually not that bad. Because we know that volume V is equal to H times X squared. So that means that the volume is going to be equal to, our height is 7 at this moment, times x squared, 16. So 7 times 16 is 70, plus 42 is 112. So that is the volume at the moment of 4 inches for the square base and 7 inches for the height. So let me reread a detail from this question because it's looking unclear and I want to make sure that we have clarity. Find the rate of change of the volume of the box at the moment that it is 4 by 4 by 7. Is the volume increasing or decreasing at this moment? Oh, okay. So that since we know that V equals H times X squared, then we can do this. D dx of H X squared. That's going to give us a product rule. Equals dx volume. But we want a related rate, and we've got this bit of information here, so let's find a way to use that. So we know that it is growing. So if we wanted to measure the growth for it, we would say, what is a relation we can put for the growth of the sides and the volume of the cube? So we know that the growth is going to be, let's see, x minus 1 squared times h plus 2. So let's find a way to make that h a proportion of x. Let's think about this out loud, actually. You know what? This is a cool one. Because this is actually going to make you think in pictures here. So we know that since this is a square, right, is x by x, the only thing that's changing is the height. So I'm going to draw this line, which is going to represent the two-dimensional plane. You know, just think that it's going in that way. So that means that when h equals 1, we have h times the area. When h equals 2, we have 1 times area and 2 times area of the square, which is going that way. So h is going to be the change of x. H and x are directly related because x is changing down 1 in area, but since h is going up 2. So this is more of a logic problem than it is a related rates problem. So is volume going up or down at 4 by 4 by 7 with a height of 7? So then we know that the next time what's going to happen is it will go from, let's see, the next thing, it will go to 3 by 3 by 9. So let's just do some algebra or some multiplication actually. So 4 times 4 times 7. So that was 112. And then 3 times 9 equals, let's see, 81. So volume is going down from there. And you could actually test that with concavity, but I just wanted to show you guys that there are other ways to approach these problems, especially like ones like these, you're gonna get stuck on the test with it. So I try and explain it in a way that's so basic that it doesn't really require prior math background. So that's why I kind of go at a slower pace here. Make sure that we're not making any mistakes when I'm teaching it to you guys like I'm learning it the first time. Because you guys are learning it the first time, and I gotta make sure that I am teaching it in a way that is empathetic of that fact, I suppose. Okay, so square base, x by x, height, h. So change in height is up 2 inches per hour, change in the base is down 1 side per hour. So that means that at 4 by 4, the volume can only be going down because the volume is decreasing. The rate of change for the volume, okay, oh my God. So guys, the derivative, the optimized function of this, so if we want to say dx in terms of volume, they literally gave us the terms, both terms to start with. So, this is something that you're going to obviously overthink sometimes. Like you just witnessed, I became witness to, so 2 inches per hour cubed for volume, negative 2 inches per hour cubed. So it is decreasing. Volume is down. And the total volume at 4 by 4 by 7 is 112. So that was a pretty easy problem, right? But there's a lot that you can learn from this type of problem, because even though we set it all up, right, that didn't end up being super duper helpful. I mean, because they already gave us all the information. So the thing that you should pay attention with when approaching these types of problems is that often you don't have to do nearly as much work. And I picked this one specifically for that reason, because I remember I saw it a long time ago, and everyone in my class spent such a long time trying to do it, myself included. And, you know, you guys could have been like -2 or 112, but instead we got to repeat the painful process of going through it. So, with that in mind, let's think about those problems when we're approaching them. So my strategy for your word problems is read the problem, draw a picture, draw numerous pictures if you have to, go through, write down every detail, write it out as a number, and then write it out as a sentence. Because if you cannot put it into a sentence, you don't understand it enough to put it as a number. So when you're approaching those problems, I want you to go and make a bullet list of every detail in the problem, and next to your bullet list problem, I want you to have a picture. Make it look pretty, make Professor King have something nice to look at while he grades your paper. That's quite the opposite of fun. Okay, let's do integration. Yes. So integration is pretty much the opposite of a derivative. Some rules for integration. So this is a definite integral, x to dx, but the derivative of x is just 1, so that is 1. Now, another definite derivative, definitive derivative, definite derivative. Let's see. So this is going to be x cubed over 3, just squared over 2 equals 4 over 2 minus 0 equals 2. This 8 over 3 over 3. So these ones right here, the reason I just kind of drew that out is you don't have to put plus c for these. If I see anyone, if Professor King tells me that you guys wrote 2 plus c for an integral, I'm going to be upset. Do not let him tell me that. That should be your goal when you get into that test. No one put plus c for a definite integral. But on the other hand, if we have something like the integral of x squared plus 2 dx. And also don't forget to write dx. That's, if you don't do that, he will probably take off like 8 points from you. I'm not even joking. Every calc professor will take off all of your points for that. So here's what we're going to do. We're going to go, okay, this is an indefinite integral because there's not a number here, there's not a number there. So let's see, this we can break it up into 2 integrals, x squared dx plus the integral of 2 dx. So this is equal to x cubed over 3 plus 2x, and since it is an indefinite integral, plus c. So the definition of area in algebra is the difference of 2 graphs where one is on top of the other. Thus, the definition of area for calculus is the same thing. Nothing has changed. This is the same math, but the only difference is that you have to do integration. So, for example, if we have 2 functions, let's say we have f of x equals, I don't know, x squared, and g of x equals 2x. So let's draw the table. X, y. So this is for f of x. We'll call this f of x table, and this is the g of x table. So 0, 0, 1, 1, 2, 4. This is going to be 0, 0, 1, 2, and then 2, 4. So what that graph is going to look like is this. We're going to both start at 0, 0. 1's a linear function, so 2x is going to be a little bit steeper. It's going to look like this, and then that is going to be the graph of x squared because it is just a parabola. And this is just a linear function, nothing special, right? So let's pretend that I drew this a little better, so it intersected that. There we go. So you'll probably find a question on the test that says, from 0 to 2, find the area between the graphs of x squared and 2x. And the way you do that is you just simply write it out as the integral of, let's see which one's on top here. So it would seem that 2x is the graph on top. So we're going to do 2x minus x squared, 0 to 2. And that's going to give us 2x squared over 2 minus x cubed over 3 from 0 to 2. And then you just simply plug in and solve. So I think that at this point in the semester, you're about to go and take the final. If you feel prepared, I think that you will do very well on it. If you don't, I would recommend just going over some of the older videos. But it's been a lot of fun this semester, y'all. And I would highly encourage, if you have any questions, before the final, just put them in the group chat. I will still be available to answer them until the final. If you have questions and you want to answer them, just feel free to shoot them my way. If you have questions you want answered, I will do it. Or if you're just curious about SI or anything like that, please let me know. It's been a fun semester, and this is it. So have a good rest of your summer, y'all.